Great.
Okay.
So, welcome to the Astronomy and Tap Jena November event. And with us, Olivia Cooper. Hello, Olivia.
Hi, Lainey.
Thank you very much for agreeing to be with us and discussing about your interest in astronomy and beyond astronomy. We'll have a very fun time tonight.
Yeah.
We have a quiz planned for later on. So I will share the link on the social media, and you guys from home can play along and hope you can find the questions. This month it's a bit spooky, okay? We have a Halloween theme, although it's November, okay? And it's the end of Halloween. We will do a spooky one for November because I like it.
Dia de los Muertos.
Yes, and then this quiz was designed by Paul Hombach and myself. So enjoy, guys. So back to Olivia. Olivia, you're not in Germany, right? Where are you
No,
talking us from?
I am joining you from Austin, Texas, where I go to grad school. I'm a third year grad student.
Oh, that's very nice. And this is the magic of doing these events online because I get
Yeah,
to speak to all these people from quite far away. It would be so difficult to get you here in Jena to talk in person. So I'm really grateful that you had time for us to do this online. And a third year student, graduate student, right? So you
yes.
study astrophysics. Uh,
Yeah.
what Tell us a bit, where are you from and what got you into the field of astrophysics to start?
Yeah. Yeah, definitely. So I'm from the West Coast of the United States, so Pacific Northwest and California mostly. And because of that, I spent a lot of time outside when I lived in Seattle, growing up with Mount Rainier in the mountains. And then I moved to a rural area in California, which was probably one of the first times that I saw the Milky Way when I was about 10 years old, moving from the city to the country. And I remember, coming home when it's dark in the evenings. My mom and I would drive up to our house, and then, I just overwhelmed by how many stars I could see, and not something I'd experienced before, but something that I felt pretty connected to since I was raised in this sort of outdoorsy way. Um, and I don't necessarily think I have the usual story where it's like watching Carl Sagan Cosmos or really into Star Wars or something. I don't have that sort of story. It's more of a just gradual figuring out that I really liked astronomy. In school, when I was little, I was always very into math and English. Those were my two main subjects, although I just love school in general, which is classic that I'm staying in academia. But I really liked math, and my whole family is in medicine, so I was familiar with sort of a science career, but not specifically going to grad school. And I explored some different topics in science when I was later in high school. And I really liked that astronomy is one of the oldest sciences. It's one of the seven liberal arts, I think. And yet there's so much unsolved mysteries left in the field, and that the history and the sort of like romantic poetic side of astronomy combined, like looking at the stars, combined with the math and physics and the unsolved mystery, that really drew me to astronomy. And then I figured out I wanted to do it by the time I got to college.
Oh, that's so romantic. Very
Yeah.
nice. No, but it's very nice and inspiring at the same time. And I think also for younger kids. And this is one of the I love astronomy for that because you just look at the night sky, right? And it's there, and it just fills you with questions about the
Yeah.
universe and how everything started and how we got here. So amazing. And in college, but in college in the US, you do different topics, right? It's not like For example, I know in Greece or in the UK, you will take a physics degree.
Sure.
But I think in the US, it's a more general, and then you have to choose your major, right? Is that?
Yeah. And my experience in college was definitely that way because I went to a liberal arts school. So I went to Smith College, which is a historically women's liberal arts school in Massachusetts. It's fairly small, and the astronomy department had like 2.5 professors.
And a half.
Yeah. And so that was a good experience for me. I really liked the personal tension and being able to really connect with my professors, and having really great advising and small class sizes, but then also at Smith, the opportunity to explore a lot of different things. So I mentioned I was into math, and I was also into English before. And I still took a lot of literature classes and a lot of English classes, and worked on my writing, because that was what I wanted to do before I wanted to do astronomy, was be a writer. And I still want to do that in astronomy. And part of it is just, the standard writing science papers, but another part of it is from a more science communication angle. And with that, I think I mentioned my climate change concentration. That was another thing that I got to do in at this liberal arts school, is focus on, I had my 2 majors, which was astronomy and physics, and that was what I knew I wanted to study and do with my career. But then I also got to work on other skills and interests that I had. So the English classes, and then climate change. And my focus within that concentration was science communication and climate literacy and education. And so I got to take really interesting classes, like a climate change class within the psychology department. And we did a lot of work in museums, and then capstone project working with local towns in Massachusetts, thinking about bringing climate to sort of policy in these rural areas, and then a climate change writing class specifically, where I got to interview really cool people working in climate change work, and work on various types of nonfiction, but still creative writing within climate communication.
Okay, I have so many questions. So many questions. I think that's fantastic. And also the opportunity that you can get to study different fields within the same degree, the college degree, and you're exposed to so many. Sorry, my Greek is influencing my brain right now. You're triggered by so many topics, right?
Right.
And also that you take yourself outside of the classroom, and you place it in the society, and you have this link from a very young age, that you interact with the society with all this knowledge, and trying to bring the knowledge from science or from climate change science to the society. And I think that is fantastic.
Yeah, and I think it's a very important part of doing science. I don't think science is really done completely or done well if it's not communicated in some way, and if it doesn't reach some audience and reach humanity, at least on some small scale, beyond just scientists and experts.
And have you followed up on this climate change thing since then?
Yeah, that was one of my goals after college, since I was leaving this sort of formal way of connecting with climate change beyond my more narrow career path. I actually founded the climate change committee within Astrobites. So
what is Astrobites?
This brings it all together. So the English classes and writing and science communication and doing astronomy and communicating the astronomy. So Astrobites is a grad student run publication, which takes papers, so science papers in astronomy, published papers, and summarizes them in brief blog posts. And it's directed, our target audience is undergrads in astronomy, so college students with some pretty minimal, like entry-level background in astronomy and at least an interest in astronomy. And I think it's pretty accessible for the general public as well, although we do target undergrads and bring astrobites into the classroom a lot. So I applied and I joined Astrobites my first year of grad school. So I've been an Astrobites writer for 2 years, which means every month it's a total just volunteer position. We just a collaboration of grad students. I think Astrobites has been around for a little over 10 years.
Oh, wow.
Yeah, so a little while now, and I've been on the team for 2 years. Every month I write a post, and I get
Nice.
to go take it. This is my favorite way of reading papers now is when I have to write
Oh,
an
nice.
astrobite, I go
Okay,
take a deep
so
dive.
I will send you when I like a paper. I will send
Yeah,
you the title, and then you can you can summarize
and I'll
it.
summarize it. Yeah.
Yeah.
So I've been doing that, and then in the past year, with a friend of mine, Suchi, we started this climate change committee because we
Okay.
were both interested in the intersection of astronomy and physics and climate change, but specifically from this science communication perspective and this angle, especially since astronomy and astronomers are usually my impression of the public view of astronomers is that we're sort of trustworthy compared to other sciences in some ways. I think we do a relatively better job at
Oh,
using analogies and metaphors.
okay.
That one thing that I appreciate about astronomers is the communication, since it is literally out of this world, the science that we're studying. I think compared to some other fields, we do try to use useful analogies. And coming from that perspective, climate science is often not seen as very trustworthy and is full of a lot of skepticism and distrust and confusion, misunderstandings, and that is, not a fault of the science that's being done or even the science communicators, but just really the human impact of climate change and the psychology of it. It's something that is impacting humans, but on a scale that is a little bit hard to imagine, and hard to bring into our daily experience, although we are seeing climate change in our daily experiences now. So coming from that perspective, I think as astronomy science communicators, we had a useful skill set for climate communication. And one of our beliefs in the a mission for this committee is that climate change touches all aspects of life and all careers, and is this issue that is relevant to everyone. And so to not keep it separate from our jobs and from our work. And so that's what we're trying to do. So paper summaries from a science context, but then I wrote one a year ago about the impact of science conferences, so
Yes,
in
I
person
saw
versus
that.
virtual,
Yeah.
those sorts of things. And then our big event was Earth Week. We brought panelists and had webinars, and that was really engaging and fun, and I think a useful time.
So that is fascinating, and seems like you do a lot of work on that and try to make astronomy a bit more green, let's say. So
Yeah.
since we are on this topic of climate change, let's stay here and tell us a bit what can we
Sure.
do as astronomers and professionals, and maybe also as general public to be a bit more green and
Yeah.
environmental friendly.
Yeah, I mean, I think what we're doing right now is even a big step talking about it, and that is something that came up during Earth Week from one of our panelists, is putting a slide at the end of science talks that acknowledges climate change is real, and that it is something we should talk about and not just ignore. And it's a point of eco-anxiety as well. Maybe people do believe climate change is real. I feel like as scientists, we're maybe on the same page as that. But it's, for me, growing up in California, wildfires are a big issue still for my mom, who's still there. And it is hard to talk about all the time and feel sort of this doomsday perspective on the world and the future, and especially as a young person thinking about my future and how possible this career will be given challenges in life. And I'm coming from a place of privileges. I have a lot of resources and support networks and can just pick myself up and move if a place becomes dangerous, but that is not the case for most people. And so I think talking about it, acknowledging it, that is perhaps even a bigger deal than the more individual actions, which are a drop in the bucket, like composting or whatever the larger corporations will tell you to do is the green way to live. I think the green way to live is to acknowledge that it's happening and engage in some way, whatever way. My way is through communication and writing, and I think other people's way is doing the science or going to climate organizations and finding where we can do the work and engage. I think that is what I think is important.
Very nice. I hope we see more written articles by you on climate change and also astrobites. That sounds very exciting.
Yes.
Do you choose topics related to what you do, or would you write about anything, for example? How do you choose the topic?
Yeah, within astrobites, I don't know if this is double dipping or lazy, but I usually pick papers in astronomy that are relevant to the research I'm doing at the moment, because I think I'm so, I'm going in deep into whatever niche that I'm studying. But a lot of people in astrobites, they pick things that are outside of their wheelhouse so they can increase the breadth of their knowledge, which is a good model. But yeah, I mean, in this organization, it's very choose your own adventure. And so the adventure I've chosen is to stick with what I want to be diving deep into. And so I do that in both my climate change committee and within my more astronomy focused articles.
That's very nice. Okay, I had one more question about climate change that it just popped in my head, because I think I read, maybe it was your article I read, or at least I followed some discussion on Twitter on that. I think the pandemic helped us a bit not to travel so much, but astronomers, we travel a lot for conferences, for meetings. And it reached the point before the pandemic that were so many conferences organized and meetings that you barely stayed at your institute. You had to travel all the time, several times a year, and some people several times a month. And that has a very negative footprint. I don't know the language you use, right? So do you think with the pandemic we learned something and this will improve, or do you think it will go back to how it was and even worse?
Yeah, it's an interesting question because I think there are arguments both ways. It is a weird perk of astronomy that we travel so much, and especially international travel, which, as you say, does make a big impact on our carbon footprint as a field. There's a few things, the operating observatories and high performance computing and traveling, and I think it's a big impact is the international travel. I think what we gained from a silver lining of the pandemic and the Zoom school aspect of things is figuring out the technology and the strategy of doing hybrid as a mode and as a worthwhile mode for reasons beyond just climate change, for general equity and accessibility of science, which is, of course, something we care about. And I think there is some nuance, because what you lose, and what people, like I've seen on Twitter as well, what people lose from fully virtual conferences is the social and the networking, and that can be have a big impact, especially on students and early career researchers. But then on the other hand, having a Zoom, virtual or hybrid mode, a lot of people run into issues of getting a visa and being able to go to meetings, or accessibility issues, either physically or financially, or other axes of impact. And so I think there is a lesson and a strategy and some tools to learn that can make doing the science more accessible for everyone and more productive. And I read a few papers for that article that I wrote, and some of the suggestions were to have hubs. So instead of traveling like all over the world for things, bringing smaller groups of people together closer.
Okay.
Maybe somewhere the Europe option, accessing places by train. We don't have that as much in America, but so having these hubs, having a virtual option, some hybrid mode, at least for the big conferences. And I think there's, still a lot of value in the smaller conferences and workshops with 50 to 100 people in meeting in person and making those connections. And I think it is helpful for the science and for people's careers. But I think it is, going back to normal, we talk about a lot, and we talk about here in my department in terms of classes specifically, and seminars and things like that. And I don't think going back to normal should be an option. I think we should set a new normal, and we have an opportunity now, and maybe in the past few months, to think about what an equitable normal would be, since we are in this transition point. I think it's an opportunity to rethink it.
Yeah, I totally agree with you. I've experienced the other side of not being able to travel because I'm a single parent, so it was very difficult for me to travel, and I was not feeling included, so I could not advance my career as easy as other colleagues of
Absolutely.
no kids. And for me, the pandemic was an advantage, because I didn't have to go anywhere to present my work and attend conferences. And for me, it was really, really good. But I also enjoy, and I think it is also very important, to choose very selectively which conferences to go to in person and interact with people, but not like all of the conferences out there, let's say, because at some point, this is what happened before the pandemic. People would go everywhere.
Yeah.
And the other thing, so I remember I wanted to present my work in a few conferences, but I didn't have the opportunity to travel because of my kid. And I was asking for a virtual talk, and I was always being turned down because they would say, oh, it's too complicated to set up, and we don't know how to do it. And it's amazing how, with the pressure of the pandemic, it happened in a week. It feels like it happened instantly, right? And now, whenever I discuss with people, with other astronomers, or on Twitter, you see some polls, I think this hybrid mode and a way to get a few people there and a few people online and try to find the best solution is the most inclusive way to promote equality and equity, because these are the two things in astronomy that we are really, really struggling, completely struggling with. There is no there is no equality. There's no equity. It's out of the window.
Yeah. And any progress that does happen feels very slow. And it is unfortunate that it seems like what it took was, global pandemic to get as a virtual option. But
yeah, but I understand what you said with researchers that cannot get a visa because the department, for example, would claim, but you have the option of attending online. Why do you need to go there? So yeah, it's not easy. It's not easy.
Yeah.
It's not easy for sure. But I think we are going to the right direction. At least it feels like that. And I really like the idea of the hubs meeting closer, so you don't have to travel so often to the other side of the world, for example. But maybe once every 2 years, why not do a big international conference in another continent? But yeah, it feels like a bit too much to go every other month.
Definitely.
I don't know. Maybe I'm getting old and I'm tired.
Well, I'm tired too. So.
I have really enjoyed traveling to Japan and to the United States and to, oh my God, Hawaii for observing. So you see guys at home, astronomers, do all these amazing things. We arrange our conferences in tropical paradise. And, okay, we are a bit privileged and spoiled. We have to say, but we work a lot, so we worth it. Very nice. That's great, but we haven't talked yet about astronomy and what you do. What got you into this field? Because you do observational astrophysics, right? You don't do theory,
right?
So how did you get into that? Was it again in college that you did some research project or?
So I was fortunate to start my first year of college, freshly 18 years old. I was in a scholarship program that gave me access to research my first year. And my first research project was with my advisor, James Lowenthal, working on exoplanet transits. And really the purpose of that project, although I'm not in exoplanets anymore, a lot of the purpose was to teach undergrads how to do research. And that was my intro to research, my intro to astronomy, and my intro to doing observational work. So there was a 16-inch telescope on the roof of our building, and we got to use that. I used that all 4 years to take pictures over the whole night of planets in other solar systems and study their light curves, so the change in brightness over time as the planet moves in front of the star. That really got me into observational astronomy, getting to use this big telescope, and now getting to use even bigger telescopes has been really fun. A lot of times that's given me the opportunity to beyond just going up on the roof, which was very fun and often very cold in Massachusetts. I have gotten to go up on mountains where telescopes often are. And as I've said before, I love the mountains. So also in college, I was also lucky enough to be in this class where we got sent to Kitt Peak in Arizona.
Oh, amazing. Okay.
With my class, I observed low mass stars for about a week. And that was really fun, scaling up a little bit in telescope size to 0.9 meter telescope.
A little bit.
a little bit, yeah. A little bit bigger objects, a little bit bigger telescope, and then eventually,
like the sun, stars like the sun you were observing in other.
Younger than the sun and a little bit smaller than the sun.
Okay.
And now I'm on much larger scales than planets and stars.
Now you
Now I study
study things with
massive galaxies, many stars and planets, yeah, that we can't see because they're so far away.
With billions of stars, hundreds of
Yes.
billions of stars, galaxies, right?
Yes.
So if I remember, you study early galaxies.
Yeah.
You
yeah.
will tell us what this is, but how did this happen? Is it common for someone to switch a topic completely?
Yeah. Yeah. So I got to do a lot of different, I wanted to try a bunch of things in astronomy. I didn't know what specifically I wanted to study within astronomy yet when I started. So beyond the exoplanet project and that low mass star project in class, I did a little bit of work with our nearest neighbor galaxy, M31 Andromeda, also an observational project at University of Utah. And then I was also at Caltech for a summer working on gravitational wave science, but sort of adjacent to that. Okay. So I was working with LIGO, so the gravitational wave detectors, but I had an observational astronomy project within that. So I used my background in light curves with the exoplanet work to study white dwarf binaries. That was another mountain I got to go up on in Southern California. I used the Palomar Observatory, the Hale 5-meter telescope.
I've been there.
Awesome telescope. Yeah, it's very cool.
This is the most, you walk in and you cannot imagine the size of it's amazing.
Huge. Yeah, so I have a picture with my arms outstretched, and it's
guys, if you ever get to go there, if you ever get to the region, go, yes, definitely go there.
It's a beautiful spot. So I dabbled in all of those, and then and I think it is typical, at least in maybe it's liberal arts, maybe it's just an US undergrad curriculum, but to try a couple of research projects, especially with the REU programs, which is like the summer internship for undergrads. So I got to dabble in some things and figure out what I liked and what I didn't like. And what I landed in towards the end of college was a project on dusty star-forming galaxies. Okay. So I'm scaling it up, looking further back in time at bigger objects, and with bigger telescopes. I was using the Gemini South telescope, which I believe is an 8-meter telescope, so even bigger, which I did not get to go to, but it's okay. It is in Chile. And so I got to use that telescope and do a project looking at the foreground lensing environments. So galaxies in front of, from our perspective, dusty galaxies in the background, and that stretches space-time and magnifies and warps the light from the background object and allows us to look further away and in more detail because we have this magnified view and stretched out view of the background galaxies.
I think we should help our viewers, and for that I will change background just for you guys. Okay, so wait for it. 1, 2, 3.
Yes. Yeah, you can see some lensing in the background, those galaxies that are sort of in arc shapes. That's not actually the inherent shape of the galaxy. There's some bright, sort of the bright white things in the foreground are in front of these more red galaxies, and it's stretching the light, and it allows us to see more detail. And so that was a project that I got involved in, and that got me thinking about dusty galaxies, since that was the target of our investigation. And that interest in massive galaxies and dusty galaxies got me interested in Caitlin Casey's work, and that is how I ended up at UT Austin working with Caitlin.
Very nice. I went there many years ago. It was 2006. I was a graduate student in Oxford, and we were working on red quasars. These are quasars, very bright nuclei of galaxies, and they're a bit obscured. So we had the project where we had to observe them with one of the telescopes at McDonald observatories.
Yeah,
So
yeah.
I went there to the west
Awesome.
part. It was amazing. It was amazing experience.
Yeah.
I observed myself, and it was amazing. The only thing I remember very vividly, actually, three things about Austin and Texas.
Mhm.
Don't mess with Texas. That's
Don't
the
mess with
first thing.
Texas. Yeah.
Don't speed, because if they catch you, you go to jail. You know, don't drive and speed. You're
Uh-huh.
done. Right?
Mhm.
And the third, Austin was so humid. Okay, you see, I have
Oh.
thought. Okay, but these are nice. These behave. They
Uh-huh.
behave
Uh-huh.
now. You know, these are in a controlled environment. I went there, and the first night, and the day I wake up, and I'm like this,
Yeah.
and very hot. It was so hot I couldn't. It was
It
all.
is a hot place.
It was, oh my
Yes.
God, it's so hot.
Yeah.
But the nightlife, the music, the
I love the
student
music.
life,
Yes.
awesome.
It's a great place to live as
Yeah,
in your 20s. I think it's just
amazing,
an awesome
amazing. I
place.
had such a good time. Closing the parenthesis. But it's good because, you know, also people can get a bit jealous about the life of an astronomer. We
Yeah.
get to travel a bit, we get to travel a lot, and get a lot of experiences, interact with a lot of people. This way, our mind opens up a bit. We are not
Mhm.
contained in our
Yeah.
town or village or within our small community. So
Absolutely.
this really helps you evolve as a researcher and as a
Mhm.
person. And for me, it
Absolutely.
was the best thing that happened to me, leaving my comfort, my house, my town, and getting out in the world. That's
Mhm.
amazing.
Definitely.
So you study things like these red things, right?
Yes.
Behind me
Red things. Yeah.
here. Uh,
Yeah.
okay, these things, but these are dusty, right? You
Mhm.
mean they have a lot of dust compared to what? To our galaxy, for example.
Yeah, yeah, more than our galaxy, but really it's about how we find them.
Mhm.
We find them based on their dust emission. So just to follow the trajectory of my work a little bit, I started with these lensed objects, and now I'm working on objects that are not lensed, so they don't have a significant structure in the foreground that is magnifying them, but they are still bright in some wavelength, so bright in some particular color along the electromagnetic spectrum, and the dusty ones that I study are bright from that dust emission. So there's a product of, or what goes along with the dust is a lot of star formation. There's starburst activity, so there's a lot of gas that's fueling a lot of stars being formed. And those stars are young and hot and emit a lot of high energy radiation in the ultraviolet range. And then that gets intercepted by dust, so larger molecules in the way, sort of like soot that we're familiar with. This interrupts the light from the stars, and the dust gets heated up and then re-emits at longer wavelengths. So in the far infrared, which is where some of my work is. And so the galaxies, instead of being bright in the ultraviolet, which would be their intrinsic radiation from the stars, they're bright from the dust. So they're bright from that heated dust, which acts as an invisibility cloak for the starlight, but then re-emits that light, reprocesses it into longer, more red wavelengths. And so then finding these galaxies that before with telescopes like Hubble HST are invisible or completely dark to Hubble, are very bright in other wavelengths. So if we go to those wavelengths and use like radio dishes instead of telescopes, like optical telescopes, to study them, we can figure out what's going on with these. So they're bright, but in a different sense than what we're
Okay,
used to.
they're not bright with our eyes, right? It's not in the
Right.
visible. Our eyes see in the visible range, and these are
Yeah.
hot, more hot, right? So
Yeah, yeah.
where you see an infrared camera, and I think if you see some applications, apps on the phones now, they have this infrared camera, so you point it to someone and it shows how much hot you
Right.
are or
Yes.
cold you are, right?
Yeah.
Have you seen this? Nice. Okay, so these are very far away, right? They're not.
Yes.
They're not like in the neighborhood, like Andromeda or the
Yeah.
Magellanic
Right.
Clouds. You are.
Mhm.
They are far away when the universe was how many years? Like
Yeah. So I
approximately.
am typically in the, I think I'm maybe the only person who says this, but cosmic morning. So we have
Cosmic
cosmic
morning.
dawn and we have cosmic noon.
Okay.
Cosmic dawn as in like the first lights turning on, so the first galaxies. Cosmic noon meaning redshift 2-ish, where there's the peak of star formation activity in the universe and all these fireworks going off. And I'm interested in the in-between parts. So we have some galaxies, they're starting to turn on. How did they get from there to the peak of activity in the universe? And that is sort of encompassed by the first 2 billion years out of 14 billion years.
Right. Still, there's a lot of time to, a
There's a
big
lot of time.
chunk of
Yeah.
time to
It's
study.
a chunk of time and a lot, it appears that a lot has happened within that time. And one of the questions that the umbrella that all my work falls under is how fast did it get going, and what did these bright and early galaxies, which is sort of ties in with is the universe a morning person, and thinking about this cosmic morning time period, what did these bright and early galaxies have to do with that process and how quickly it got going?
So you tell us that they grow a bit faster than galaxies that are formed later on.
I think that is one of the questions that we want to answer. And I'm looking at, in my research, I have a few different projects and they look at different populations of galaxies. So one is the dusty galaxies that are bright in these infrared, bright from the dust at these long wavelengths. I also study galaxies that are bright in the UV, so from starlight, but are embedded within this like neutral hydrogen soup, and then they have islands of ionized hydrogen, which, getting into the nitty gritty a little bit, but bright in another way, and a different population of galaxies from these dusty galaxies, but maybe they're connected, and thinking about how they're all connected by being massive and having some amount of activity going on. How did they get going, and then what do they do next, and how are all these populations connected?
That's very nice, and actually ties very well with the discussion we had last month in October, the October event, with Rebecca Larson, because she works on the ionization islands. So this is a bit after, right? So at that moment when they start becoming bright, and then after how they form, what is happening. So we are covering
the evolution.
The evolution, right? The evolution. And guys, this is what we were talking also last month. This collaboration that we are all in is the Cosmic Evolution Survey. We are promoting it, yes.
Yes.
Shameless self-promotion.
Yes.
But it's the best.
It is the best.
It studies exactly that, right? How from the first galaxies, when the universe was young, we ended up in galaxies like in the universes today, right? How did we end up in our Milky Way? And how do galaxies look when the universe was young? So Olivia is trying to answer all this.
Yes. All these questions,
and you still use a lot of telescopes, big telescopes, right?
Yes.
And also, will you use JWST data?
Yes. Okay. I am very excited to use JWST for all these different populations that I'm talking about. It'll be very relevant. So the project I'm really embedded in right now is probably very similar to what you talked to Rebecca Larson about. last month is looking at these reionization era galaxies, these ultraviolet bright galaxies, and trying to find and see if they live in these big bubbles of ionized gas. That is directly connected with JWST. All the fields that I'm looking in are in JWST fields. So Cosmos is one of them, Cosmos Web, which is the JWST coverage of the Cosmos field. I will be tying together the big JWST surveys with these more targeted searches for massive bright and early galaxies within these fields. And then on the dusty side, looking at trying to tie together with various telescopes, so JWST, and then also ALMA, which is in the infrared wavelengths, far infrared, tying these together to put together pictures of galaxies, their gas content, their dust content, their stellar content. So yeah, JWST will be very, very relevant. I feel like I got lucky with the timing of grad school.
Yeah. It's
it happened
it's
to launch while I was here. Yes.
The golden era of infrared astronomy.
Yes.
Sorry, I had the question, but it just it just flew. No, I just wanted to mention something for our viewers. If you don't know where ALMA is, it is in Chile. It's not in space. It's on the Earth.
Yeah.
And it's amazing. It's on a desert.
Mm-hmm.
Yes, I've never been. Have you been?
I have not been. I would love to go. I think it's an intense place to visit, but it is an amazing instrument, an amazing telescope, array of dishes, and it's, I would say, the best at what it does. So having JWST and ALMA together will be really amazing.
Fantastic. Well, best of luck. The Cosmos Days are coming in December.
Yes.
And guys, also in the previous event, Rebecca mentioned briefly about our outreach and another shameless promotion.
Yes.
Olivia and I are coordinating the outreach for the Cosmos Web. So stay tuned, because there's going to be a lot of information coming your way from our social channels.
There will be a splash.
There's going to be a splash. Going to be crazy. No, really, we are super excited, and you're going to see amazing images from this telescope. So stay tuned.
They're going to be huge. They're going to be huge.
Yes, early Christmas present for us. Yes. Amazing. So Olivia, two things. Where do you think that your work will, I mean, you are trying to find these early galaxies and study their properties, but why? I mean, what do you think you will discover something that we haven't discovered, or why would someone want to study this object?
I think, I mean, why massive galaxies, why bright galaxies? The bright and the massive sort of go hand in hand. The brighter, more massive galaxies are usually the more rare galaxies. The smaller, fainter galaxies are typically the more common population. And so looking at the more extreme end of things, which is sort of where I live in my science, is these dusty things are extreme, the UV bright things are sort of extreme. That's sort of like the edge of what's possible. And so it's a really great test of our models of how galaxy evolution happened, how cosmology is happening in these early times. And I think, going back to JWST, part of the exciting thing about it is we don't really know what we're going to find. And so I think there are questions I'm really interested in, like I talked about, connecting all these different populations and looking in different wavelengths, trying to tie together a bigger picture of galaxy evolution on the massive end of things. But I'm excited for JWST to give us questions we didn't even have yet. And then, maybe we'll get the answers with a future instrument. But those new questions are really exciting, and we don't know them yet.
It sounds fascinating. I cannot wait to see the results coming out from these studies. It's a period of time that we don't have a lot of information about.
Right.
It's very hard to see.
It's far away.
It's very far away in the early universe, and we needed a space telescope in the infrared to be able to access that period of time and space. Excellent. So my last question, because I don't want you to get too tired, because we have a quiz coming, and I want you to be fresh. Right. So, what is my question? Yes, I asked this because I want to know everyone how they think about this. What do you think is going to be the next big discovery? It doesn't have to do with your field. Anything that you think is going to be the next anything.
Yeah, well, of course, I'm thinking about my field, and we're talking about JWST. So the first thing that pops into my mind is there's kind of a flurry of papers coming out with trying to get the record breaker sort of most distant galaxy that we know about. And that is, that's exciting. And I think there's a lot to still disentangle within all that work. But in the initial data sets that we have, we're looking deeper than Cosmos Web, but in a smaller area. And what we need to find the most extreme things is a larger area, just in a statistic sort of perspective. And I'm excited for Cosmos Web to probe that larger area. Although it won't go as deep, I think it's likely to find these really rare objects. So I think that is what the next thing in maybe December, but maybe once all the data are taken a little while later, that might be the next big thing, is finding really rare objects, either super distant galaxies or galaxies that are more massive than we think was possible, or galaxies that have a large quantity of dust earlier than we thought was possible, or galaxies that were totally quenched or turned off, all their star formation just shut off earlier than we thought was possible. Pushing the limits on our models in that way by probing a large patch of the sky. I think that is where we have stuff to learn and find.
Fantastic. Okay, I'm crossing all my fingers.
Yes.
Really great. That was amazing. Guys, if you have questions, write them in the chat. We will get back to you in due time. Now, are you ready? Okay, I will change one more time my background, because I liked the blue one a bit more. It goes with my laptop. So excuse me. There you go. And now that I'm ready, I'll drink a bit of water. Are you ready for the quiz? Okay.
I guess, yeah.
I also don't know all the questions, the answers. So I have my cheat sheet here. If you can see, Oh no, I'm giving the
not really.
Oh no. Right. And before that, guys, subscribe, like, share on the social media, and follow us everywhere. I have Astronomy and Tap Jena on everything: TikTok, Instagram, what else? Facebook, Twitter, YouTube, where you're listening to this now, watching. Right, excellent. And Olivia will give me the links for these papers on climate change that they wrote, and the astrobites link. So we will put them on the description, so you can have a look and educate yourselves. And you should read those astrobites articles; they're very nice.
They're quick.
Yeah, they're accessible. I think they're very accessible to everyone. You don't have to have a specific knowledge of the field, of the specific field. That's why I really enjoy that, and I think this is a very, very good idea to do that. Right. So let me share my screen. Ta-da! Okay, are you ready?
Yes.
Ta-da! So guys, you have to fill in your email, and then at the end, click, and then at the end, send me, and I will release the answers when you have completed everything. So let's start. Oh, this is a bit dark. It's a
Okay.
very dark exoplanet. This is exoplanet TRES2b. It's a beautiful name.
Mhm.
It's like Elon Musk's kid. The same concept. This was discovered in 2006, and it has eternal darkness. It's very spooky.
Mm.
It's a Jupiter-like planet, so it's gas planet, okay? Very close to its star, sorry. And the air is as hot as lava. True or
Wow.
false? True or
Oh my
false,
gosh.
Olivia? True or false?
There's a lot to unpack in this question.
Yes, yes.
Well,
Didn't you see? I'm not bluffing. It's called no poker face.
um,
This is
well,
not
it
the actual
sounds,
image. It's an artist impression, by the way.
yeah,
Yes.
yeah. It sounds like it's close to its star, so that makes me think it's not an eternal darkness. So I'm going to say false, but I do, I believe that there's some planet with eternal darkness.
Yes, but it has a lot of gas.
Okay, has a lot of gas.
Yeah.
Eternal darkness on the surface of the planet.
The surface, gas planets don't really have
Yeah,
a surface,
yeah.
right?
Uh-huh.
Yes. So
I'm thinking too
it's a
hard about this
tricky one.
question.
It's a tricky one. It's a tricky one. So the idea behind it, well, as I read from the NASA website, because they have a very nice page with all these spooky objects.
Mhm.
I will put it on the description also. Is that
Okay.
yes, it's very close to the star, so it's very hot, right?
Mhm.
So the last one there is as hot as lava. Makes
Mhm.
some sense because it's very hot to its very close to its star. But because of these clouds, the light that
Totally
goes that
opaque.
doesn't go in, the light doesn't
Uh-huh.
go in a sense. So it's like eternal darkness. But they also think there is like this reddish kind of light that a bit of light manages to go in and then scatters and it becomes a bit, dark-ish.
Okay.
you
Yeah.
know.
Yeah. Uh-huh.
Um, so it's true. All the
It's
statements
true.
are true, and it's a
Yes.
very weird planet because you wouldn't expect something like that. It has
Yeah.
very
Yeah.
weird properties compared to other gas planets. Yeah,
Yeah. That is very bizarre.
yeah, very, very bizarre.
Spooky.
Truly spooky, and the air is hot as lava. The floor is lava, the air is lava. Okay. Next. Good.
Which nebula is
Which
this?
nebula is this? Okay, wait a minute. Okay, Ghost Nebula, Little Ghost Nebula. Okay, that is the same. I'm sorry, I don't remember how I made this question. Or the Skull Nebula. It doesn't
Um,
look like a skull. No.
I don't see the skull. I think
No.
well,
Go.
Ghost Nebula is my guess.
Yes, yes, it's a ghost. It's like a
It looks like a wispy, yeah,
ghost.
like a kid's ghost Halloween
Yes.
costume that's just different.
Halloween, yeah. Maybe this is the little ghost nebula.
Yeah, those are the
It could
little
look like
ghosts.
it could look. I don't remember which one is the little ghost nebula. I'm sorry, guys. I failed you. Okay, let's move on. Oh, very nice. Oh, I
The
like this
Witch's Broom
images.
Nebula.
Okay, so the Witch Broom Nebula is part of. Okay, Carina Nebula, Trifid Nebula, Veil Nebula, or Flame Nebula.
Wow.
Nice names. Very
Yeah.
a lot of imagination. Look at the shape. What does it look like to you?
Yeah, it kind of looks like the Carina Nebula to me. I'm trying to think if it matches my image in my head.
But
But it looks more like a flame or a veil.
it looks more like a veil, doesn't it?
I think it
Because
looks
it's a
like a
bit
veil.
flowy, isn't it? So
Yeah.
imagine wearing, like these little things here in the
Mhm.
front. It's like
Yes.
a veil. Very nice, very nice. Good. Okay, now that I made a fool of myself, yes, it is the
The
Veil
Veil Nebula.
Nebula. And
Awesome.
it's a very spooky witch broom nebula. I have no idea why they called it Witzbloom Nebula. I do not see.
Yeah, there's kind of a skinnier part and then it like flames out towards
This one and this. I like a. Oh, I got it. Okay, like in Harry Potter, like
yeah,
the brooms they use for Quidditch. What's the game?
Quidditch, yeah.
Yeah. Okay, good. Now I got it. Nice. Okay, now we will do something different.
Oh,
The first time
okay.
I do something like that here. So we have a sonification. We will click for the sound and we will play it. And then you have to tell me what it is. So the four options are the atmosphere of Mars, Voyager in space, lightning in Jupiter, or the sun. So sonification, one of these things. Let's listen. One more time.
I can't really hear it on my end, so I might play it from my
Oh,
computer.
you cannot hear it. Oh, how can I fix that? That's not good.
I will play on my computer.
Yeah, that is really, really, really lame.
Okay, it's sort of like a whistling. It sounds like cars going by or something.
Oh, I should fix that. That's horrible. I'm sorry, guys. Amateur. Zoom amateur. I know there is a trick on that to share. So bad, so bad.
It's okay. I could hear it on my computer.
You could hear it on your computer. Let's
Yeah, if I
finish
play it myself.
for the audience. Give me a minute. I have it here. I have it here. I have it here. It's okay, guys. It's okay. Just drink some beer while you're waiting for me. Horrible. Yeah, okay, yes. I'm not a robot. Did you hear it now?
No, I can't hear it.
No, at all. Well, you hear my voice. What?
Yeah, weird.
What is going on? No?
No.
Guys, we failed you at home. Play it on your own.
Yeah, well, play it on your own computer.
Play
It'll
it on
work
your own
that way.
computer. Technology has failed me. I'm gonna go and cry in a corner. So anyway, what do you think it is? Is it
Yeah.
atmosphere of Mars? I will help you. Don't worry. Wait. Is it the Voyager in space, lightning in Jupiter, or the sun? So if you listened, you would hear that it's not the same throughout, but it has some
Variation.
variation, especially towards the half end, something like spiking. So what could spike? Like,
well, that seems like a hint towards lightning in Jupiter.
yes, okay. Yes, it is. It is
Nice.
lightning in Jupiter because you hear this
Sort of whistling. Yeah.
yes, and then you have the high pitch. Just to say that sonifications, in general from data, they take the data, so they're usually light curves in some frequency, and then they allocate some notes to that frequency, and then they make a song out of it, right?
Yeah.
We can do it with images like the one behind me, and it depends how you do it. Sometimes they have, so NASA has a very big repository of that. So it can go from one side to the other, and then you hear different little things popping. Or it can be some supernova remnant that can go circular, for example, and then you hear the different peaks in the intensity along this outer shell. or inner cell. It depends what they do. And it's fascinating, really. Or I heard once, actually, my collaborator, Paul Hombach, is a musician. So he makes sonifications of transits.
Very cool.
Yeah, Venus transit on the Sun and Mercury, and it's fascinating, really, really.
Yeah, they do it. So Astrobites has a podcast called Astro Soundbites, and they do have a sonification section within every episode, which is very cool. And the podcast hosts are getting better and better at identifying what it is. I'm not very practiced at it.
Okay, so let's practice a bit more now.
Okay.
Because the next one is again a song that we will never hear from this, but you have to. I will
play it.
Okay, I will try to play it. So you have to listen for, is it a star, a nebula, a supernova, or a lensing galaxy cluster, like the one I had behind me before. So usually you would hear a lot of things popping up. So what is it? Where is it? I will find it. Open Sesame. One more time. Maybe you can.
Well, there's a lot of popping sounds.
It's like a pulse, no?
Yeah.
It's like
Yeah.
kind of.
Yes,
Yeah.
like a video game.
Like a video game, yes.
Yeah.
So what do you think it is? That's a bit tricky, I think, because
yeah, it's a little bit tricky.
Yeah. The description they had on the NASA SoundCloud was the answer. But for me, it was not obvious, for example. Or like, I would think this would be like a pulsar kind of thing because it reminded me pulse, but they didn't have a description of a pulsar.
Yeah. Well, I think it sounded sort of like random, not uniform thing, random distribution of things, which makes me think it's a cluster, a galaxy cluster. The other three are maybe a little bit more like uniform.
Okay. So you see, I told you it was tricky because it is a star based on their description.
Oh, okay.
But when I heard it, I was either thinking of a pulsar, but I've heard how a pulsar sounds, and you really hear the pulse. So if you get
very regular.
data, yeah, you get data from VLBI, for example, you really hear the pulse, like you will hear it. This one was very different, so I don't know how they made this sonification, but it didn't remind me of a star. And because of this, as you said, there are a lot of popping things.
Yeah.
It was something like that, like going across a field.
Yeah.
But there you go. This is what it was. I will put the link of the sonification so you can also, guys, listen to them. They're very, very nice. And NASA has a list in SoundCloud, yes, of many different things, even from Voyager and from sounds in space and many spooky things. It's very nice. Space sounds very, very, very spooky. So this brings us to the Witch Head Nebula. This is different. It's not the broom, the head, because you see it has like a witch kind of head shape, whatever. So we want to find out in which constellation it is. Is it in Orion, Cygnus, Eridanus, or Gemini?
Wow.
Like 20% chance to find that.
Yeah, I don't.
Chance. Yeah.
The only one I'm familiar with really is Orion and a little bit Gemini. And so I feel like I just have to guess something. I don't think I know there is, a lot of young star formation going on in Orion.
Okay, yes, and here you have a lot of stars.
Yeah, but I don't know if this is in Orion, but I guess that would be my guess.
So Orion.
Sure.
Yes, very nice.
Yay.
Yes, it is in Orion. Actually, the logic behind how you get it is very good, even though you didn't
Thank
know
you.
the skills, because you see all these little stars, guys. So, these are regions where stars are being born and formed, and there is a lot of things happening. So, there you go. I mean, even if you don't know something, maybe you can have a think about it and eliminate other options. This is how we do astronomy. Right. Okay. This is another planet. Okay. So this is KOI minus 55b, another Elon Musk kid. So it was discovered in 2011. It was a Jupiter-sized planet, but oh my God, poor planet, poor exoplanet. Interaction with its now dead star shrunk it to Earth size. So now it's an Earth-sized planet. Nevertheless, it's as hot as hell at 6,000 degrees Celsius. Celsius? Yes, yes. I was doing the conversion in my head. Yes, Celsius. And hotter than the sun. Hotter than the sun? Hotter than the sun. Hotter than the sun.
Okay.
Hotter than the sun. So how hot is the sun?
The sun is 5,800 Kelvin, I think. So
Kelvin.
about
Okay, Kelvin.
Kelvin. So that sounds like approximately the temperature of the sun. I don't know if this is a trick question.
So it's either I wrote down this wrong or the information on the website. Okay.
Okay.
Damn it, I should have looked how hot the sun is. That is horrible. Fail. Yes, apparently it is true.
Then it's hotter. Yeah, maybe a little hotter.
But so it depends which part of the sun we are talking about, because the atmosphere is hotter than the exosphere.
Yeah.
So I don't know which part of the sun they were referring to. So maybe it's true if you're referring to the corona, for example,
Yeah. Yeah.
which is cooler than the photosphere. But I thought the photosphere is less than 6,000. Is it around 6,000, really? Google.
So
Okay.
I'm Googling it.
Temperature of sun. No, it's 5,000 Kelvin. So that's in Celsius, it's less. Oh my God. In Celsius, yes. Oh, it's around.
Yeah.
Okay.
Around the same, but I'll allow it.
Okay. Yes, there you go. Excellent. This is why we have Google, and this is how the sun is written in Greek, guys.
Nice.
It's called ήλιος.
Helios.
Ήλιος, good. Right, so we close this, we got this. This is also an artist impression. We don't, only with JWHD we will get direct images of exoplanets. So this is the
And
other.
they won't quite look like this, but
It won't look exactly like this. No,
yeah.
no. Maybe the next generation JWHD.
Sure.
Okay. Let's get this going. This is NGC 2080. The Ghost Head Nebula has a particularly spooky look because it is a dark nebula, reflection nebula, supernova remnant, star-forming region.
I'm gonna guess star-forming region. Looks like some bright spots in there.
Very nice. Correct. It is correct. Yes.
Nice.
So you have a lot of dust and gas, and this is what you need as a fuel, right? To make stars, and you have a lot of things going on here. So maybe stars behind it, illuminating it, right?
Yeah. Spooky.
Very nice. Spooky. Yes, and green here. Ooh, spooky.
Yeah.
Okay. Excellent. Oh, another sonification that will fail. Let's go back to the next one. I'll play the next one. So we're looking for galaxy, the sun, planet, the edge of the universe.
Okay.
The edge of the universe. That was funny. Maybe.
Okay, it's a very deep humming sound that goes sort of stronger and weaker. It's pretty uniform.
Mhm.
Okay,
Okay, so
I'm gonna guess planet.
planet. Okay, do you want to guess again?
I got it wrong.
Listen. So listen. So it was like there was like some. It was uniform. You were right, but there was some ups and downs, like but also something like like reflecting kind of
Reflecting.
thing.
Okay.
So, not reflecting. How do I say? Yeah, for me it was like standing waves, kind of thing that could be translated into something. Okay, this is very difficult. I realized my description is very difficult. It's not a planet.
It's not a planet.
It's not the edge of the universe because
No.
we don't know. We don't know. We cannot see the edge of the universe.
So it's between a
Between
galaxy and the sun.
and the sun.
Is it maybe something with like a spiral galaxy?
No,
No, it's the sun.
it's the sun. It's the
Okay.
sun. For me, if you're a bit familiar with asteroseismology and the waves
The
inside the
waves.
sun, this is what it reminded me of. But it's not. It's very difficult. It's not so clear. I think the fields that that you have like the Hubble Deep Field.
Yeah.
Nice, but I couldn't get the sound for the Hubble Deep Field to download it, so I'm sorry. Oh, right. So this is the coldest place in the universe, maybe. True or false? The ghostly Boomerang Nebula is the coldest place in the universe.
Well, this seems like a meme, but I'm gonna guess false.
False. No, it's true.
It's true.
Well, yes, there was an article. I will put the link. Apparently, it is colder than the mean temperature of space.
Okay.
2.3, 2.7.
Yeah.
Kelvin.
Colder than that. That's very cold.
Just a little bit colder than that. Yeah. So, yeah, you would not expect it, right? Apparently, they found it. I don't remember the error in the measurements. So,
important question.
yes. You see, astronomers, we judge everything. We question everything. Oh, look at this one. This is another exoplanet, WASP 12b. It was discovered in 2008 and is an egg-shaped exoplanet. So the reason for the shape, it's like, it's a bit elongated, but a lot elongated. It's not, even our Earth is a bit, elongated in some way, but this is like an egg, very, very stretched. So what is the reason for that? Aliens in this planet like eggs. Maybe.
Yeah.
Yeah, why not? It is very far from the star and thus being stretched. It is very close to the star and thus the star devours it slowly. It's okay, that's a typo. It's two planets. It's two planets that collided and now slowly becoming one.
I think this planet is close to its star and is under the gravitational influence of the star.
Yes. Very good, very good. So if you were in this planet, I'm sorry, but you are going to get eaten by your food. And I think that's our last one. Yes. So I hope you have been following the DART mission. In the previous quiz in October, we had a question about this. So that mission was supposed to hit an asteroid and take it off course as the first test for planetary defense. Okay, and NASA is and CSA, yeah, the Canadian Space Agency mission. So there were follow-ups, you know, telescopes. They were following up Dimorphos. Dimorphos is going around in orbit from Didymos. So Didymos is in the center, Dimorphos goes around. So DART hit Dimorphos and with the purpose of changing the orbit to making it a bit smaller so it goes a bit faster, you know, so to deflect it a bit. And this is the image we got. And this is the tail, so a big dust tail. So this is Dimorphos, and this is after the crash, after DART crashed on it and got destroyed, of course. Dimorphos changed its orbit. It became less, the orbit became smaller, less time to go around Didymos, and it now it has a tail like a comet. So
yeah.
What surprised the scientists? It became a bright radio source. It began to rotate in retrograde direction, developed an Earth-sized dust tail, or turned into a micro black hole.
Well, based on the picture, I'm going to say the dust tail.
Yes, apparently, did I write it? Yes, this is a huge tail. Is around 6,000 miles. Since we are in the US now, I say it in miles. And the Earth is around 7,000 miles the diameter. So you know, quite similar. Yes. So there you have it.
Cool.
Huge. And it worked. The experiment worked. The test worked.
Yeah.
And congratulations to all. Fantastic. That was.
All right.
Did you enjoy that, Olivia?
Yeah, it was fun. I love the sonifications, although I'm bad at identifying them at the moment.
Oh, me too.
I'll work on it.
You know, I will send the links for the sonifications. Also, there are a lot of sonifications on YouTube, which you can listen to. It was a bit tricky to show them here because the name is right there, so you cannot guess. It would be easier to do this in the pub where you don't look at my screen or have another laptop, which I didn't. But anyway, I'm glad you liked it. I had a lot of fun. Thank you very much for
absolutely. Thank you for having me.
It was amazing. I learned a lot of things, and thank you for sharing your experience and your knowledge with us. Guys at home, like, subscribe, follow, you know, everything, and stay tuned. And we see you soon. That's it from us.
Awesome. Thank you.
Thank you very much. See you later. Bye.